Welcome to section 12.6, the binomial theorem. We're going to work with the binomial theorem and Pascal's triangle and learn a couple other things along the way. Might even have some fun. Well, let's get started with an old problem that you might have seen in your algebra before this class, and that is finding a plus b squared. Now, contrary to somewhat popular belief, you can't just square this and square this. You got to square the whole thing, which means multiplying it by itself. And then from here, we'll FOIL things out. And you'll notice that the middle two terms add together, and I get a squared plus 2ab plus b squared. So there, not so bad. The question is, well, what happens if I want to do a plus b cubed? And that starts to become more of a problem. A plus b cubed would be a plus b times a plus b times a plus b. And boy, multiplying that out becomes a lot more work. And you can do it, but the goal of this section is to help you find a more clever way to do that. And that more clever way to do that is with something called Pascal's triangle. So let's talk about Pascal's triangle and take a quick look at who Pascal was. Blaise Pascal was a 17th century French mathematician. He did a lot of work with probability, but his name sticks a lot with Pascal's triangle, and that's something that helps us expand these binomials. So if you look at it, anything to the 0 power is 1, then a plus b to the first power is just a plus b. We did a plus b squared. Here's a plus b cubed. Cube that out, then you get something, wow, it's not a cubed plus b cubed, that's for sure. But there's a pattern in here. And you can start to see that if you strip away all the variables and just look at the coefficients. So let's just look at the coefficients here. These coefficients are Pascal's triangle. So, okay, it's kind of neat. But how do you get from one level to the next in Pascal's triangle? It's a good question. Let's take a look at that and see if we can't figure out a few more things about Pascal's triangle. Now we're going to start out with a 1, and then a 1, and a 1. And now on the outside, we're always going to add 1, make this bigger on the outside. But these inside ones, to get the next number here, I'm going to add the 2 numbers above it. So 1 and 1 gives me 2. For this next row, I'll put 1s on the outside, and now again, add the 2 numbers above it. So 1 plus 2 gives me 3. 2 and 1 also gives me 3. Now what you will see when you do these things is a lot of symmetry. Pascal's triangle will be symmetric. So can you tell me what these 3 are going to be down here in row 4? Hopefully you said 1, 4, 6, and 4. All right, your turn. All by yourself. See if you can't do row 5. Okay, that's a good enough head start. Hopefully you start with a 1 here and a 1 here. Between these two, add those up. We get a 5, then a 10, 10 again, and another 5. And this would be useful for helping us figure out, say, a plus b to the 5th power. So yay, that's pretty cool. Now, the question is, what's this like in general? And there's a nice general formula for that. So let's look at that general formula, and here it is. And wow. So if you want to expand a plus b to the n, you get all this mess. And I'm sure that a lot of you looking at this are probably saying to yourself, hey, welcome to Facebook. But it's not going to be all that bad. We just need to take a little time and understand things. And that's going to start with understanding what this thing is all about. There's a factorial notation. So n with an exclamation point. And that's probably best explained by telling you what 4 exclamation point is. So that's going to be 4 times 3 times 2 times 1, which is 24. And basically, if you had 4 objects, what this is telling you is the number of ways you can arrange those 4 objects. Now, I'm kind of disappointed that I'm not doing this face-to-face with anybody, because usually I like to talk about this in terms of being in an English class and being in a math class. This is the fun part. If this was an English class, this would be 4, but it's a math class. So it's 4 factorial. So n factorial is what this is. And this formula is used to help calculate the coefficients in Pascal's triangle. Now, you don't have to use the formula. You can write out as many levels as you need. Just unfortunately, for some of the last couple of problems that we're going to do here in this section, that would become a real pain. So it's helpful to learn some of the notation here involved. And the notation is actually kind of cool because it gives us a chance to understand a little bit more about math, and it has some nice applications. So it's this formula down here that I'm looking at. What are these coefficients in general? Okay, so it's n factorial over k factorial times n minus k factorial. Oh my gosh, that looks pretty bad. Let's work with it though. Okay, so n choose k, n factorial over k factorial, and n minus k factorial. The cool thing is this, one of the interpretations of this is the number of ways to choose k objects from a group of n objects. And let me give you a nice example here. What if you're playing cards? You have a standard deck of 52 cards, and you're going to choose 5 of them. So 52, choose 5. So 52 choose 5 would be 52 factorial over 5 factorial times 52 minus 5 factorial. Wow, that's a lot, you know? So let me show you how to do some of these things on your calculator. And let's do that here on our screen. So I'll clear out some of this stuff. So I don't think you want the calculus. Clear that, yes. And beneath here, you'll see the key history so you can follow along a little bit with what I do. One of the things I'll need in this calculation is a 5 factorial, which is just 5 times 4 times 3 times 2 times 1. But rather than do that, make your calculator do that. So how do you do that? Well, let's type in the 5 first, and then hit the math key. You want to go over to probabilities. So you can cursor to the left twice or to the right 3 times, either one. But down there in the 4th option is your probability, or you can use your factorial. So 5 factorial should be 120, bam. But wait, it gets even better. The notation that we have here on our page is also thought of in a different way. Sometimes n choose k can also be thought of as n choose k like that. And that's the notation that your calculator recommends and recognizes. So let's take a look at how you might be able to do something like this on your calculator. So we wanted to calculate 52 choose 5. I recommend that you type in the 52 first. So let's do that, 52. Go back to the math. And if you're heading over to probability, then your instincts are steering in the right spot. And there you go. The 3rd option down is NCR. So let's do that one. Press enter. Now, how many do we want to choose? We want to choose 5 out of that group. There should be about 2.6 million different 5-card hands that you can deal from a well-shuffled deck. There you go. So just under 2.6 million. Nice. Let's do one more like this to practice this one. And the next one I'll take a look at is, let's see here. There. The next one I'll look at is 47, choose 6. Now, I'm not much of a gambling man myself in terms of lottery and stuff, but with the state's lotto, there's 47 numbers. You have to match 6 of them. So let's figure out how many different ways there are to choose 6 numbers out of 47. So that would be 47 factorial over 6 factorial times 47 minus 6 factorial, which would be 47 factorial over 6 factorial times 41 factorial. Probably be a pain to do it that way. So let's just do it this way and find out how many different possible combinations there are of a winning lotto ticket. How many different ways can those numbers conspire to make a winner? So we'll go back here to this menu. We're just going to the graphing calculator. I'll clear this out and clear this out. We'll start with our number, 47, then hit the math key. Where from there? Good job. Order probability, then down to NCR. You can just type the number 3 if you find that convenient. Then I'll type in a 6. There should be about 10.7 million different possible winning lottery tickets. Wow. So what does that mean? Well, it means I somewhat agree with the state's lottery commission who hosts this webpage, but it also means that your chance of getting struck by lotto are far less than your chance of getting struck by lightning. Sorry to break the bad news to you, but keep playing the lottery because it supports your state's education program. Thank you, well done. Let's get back to Pascal's triangle and using it in solving some of the problems that you're going to face when you do your homework in this section. So let's take a look at a nice simple one to start with, a plus b to the 4th power, and understand the patterns in this. So let's start out with the a. I've got these 2 terms, a and the b. So we'll start out with a to the 4th, and then I'll follow that up with an a to the 3rd, and an a to the 2nd, a to the 1st, and then a to the 0. So notice that they're decreasing in powers. But at the same time, I need something else. I need my powers of b. B is going to run in the opposite direction of A. I'll start out with b to the 0, b to the 1st, b to the 2nd, b to the 3rd, and b to the 4th. Probably should put a little plus sign in here as well. Actually, it's not exactly the ideal spot for that plus sign. Okay, there's one thing missing though, and that one thing missing is the coefficients from Pascal's triangle. So let's see if we can't figure out those. Now, we can just go back a little bit to our previous page and look at the 4th level. 4th level of Pascal's triangle looks like this. So the coefficients I need to put in are 1, 4, 6, 4, and 1. I think I can remember that. Let's squeeze those in. So I have a 1 here, a 4 here, 6, 4, and 1. Last but not least, let's clean this up. So to clean that up, well, I don't need, you really need to write the 1, so it's just going to be a to the 4th. B to the 0 is 1. plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. Wow, that's a lot more fun than writing out a plus b times a plus b times a plus b times a plus b, and then multiplying it out, collecting like terms, and eventually getting this after a good 10 minutes worth of work. Nice. Let's try another one. What's going to start happening though is you're going to have different terms other than just a and b. So we're going to try and make this more general so that it doesn't just apply to a very special case. So let's look at a problem like this one. X minus y to the 5th power. So we'll do this one, for example. This one's out of your homework. And you might want to think of this as x plus negative y to the 5th power. Because what that's doing is it's kind of giving you your a and your b. So let's start out with the a term and the b term. And my exponent up here is a 5, so I'll start out with x to the 5th. And then, let's see, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and finally no x's at all, x to the 0 if you'd like, plus x to the 0. On the flip side of things, I need to do the reverse with the y's. So it's going to be negative y to the 0, negative y to the 1st, negative y to the 2nd, negative y to the 3rd, negative y to the 4th, and finally negative y to the 5th. I ran out of room here a little bit, so you have to pardon me, I wrote it in a different spot. There's one last thing that I need, and again, that's the coefficients from Pascal's triangle for the 5th level. So that'd be this one, 1, 5, 10, 10, 5, 1. So let's put that aside and write out some coefficients. 1, 5, 10, 5, oops, 2 10s, 10, 10, 5, and 1. Let's simplify this. Anything to the 0 power is 1. So I have 1 times x to the 5th, that's just x to the 5th. Now let's do another little simplification over here. Keep in mind that anytime you have negative y or negative something to an odd power, that negative is going to stay here. So it's going to be negative 5 x to the 4th y. Squaring things is going to make that negative disappear, so it's going to be positive 10 x cubed y squared. Cubing things, what's the sign going to be? Positive or negative? Odd exponent, negative. Minus 10 x squared y cubed plus 5 x to the 1st, y to the 4th, minus, that's a 1, that's a 1, minus y to the 5th, it's just going to be minus y to the 5th. Okay, nice. So that's another example with Pascal's triangle here. Let's keep going to make them a little bit more challenging. Try and give you a good taste of things that you might see as you're working through the homework. Let's do a cubic one. So 2 plus x squared cubed. Now cubes are going to be a little bit easier to work with because there's not going to be as many things going on. As before, you've kind of got your a and your b. So this is the A, this is the B. Let's start out with everything to the right power. It's going to start out with 2 cubed plus 2 to the second plus 2 to the first plus 2 to the 0. I didn't really leave myself any room here for x squared to the 0 power. Yeah, I guess I could squeeze it in here, but I don't want to. Anything to 0 power is just going to be 1. So I'll pick it up here with x squared to the first power, and then x squared to the second power, and finally x squared cubed. And technically there's an x squared to the 0 power, but that's just going to be a 1. Before I start simplifying, what else do I need? If you said the coefficients from Pascal's triangle, ding, 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 you got it right. So it's going to be a 1 here, then what, a 3, and a 1, which I'm not going to write. Let's see if we can't simplify all that out. 2 cubed would be 8, plus 4 times 3 is 12x squared, plus 2 times 3 is 6. Now, here's the big question for you. Do you add these or do you multiply them? In this case, it doesn't make any difference, but over here it does. So should it be x to the 5th or x to the 6th? Well, if you said x to the 6th, you're right. Good job. Now, if you were to look up your answer in a book or in WebAssign, they would probably list it in order, and that is decreasing order. So they'd write x to the 6th plus 6x to the 4th plus 12x squared plus 8. It should accept it in any of the orders. In fact, since there's 4 terms here, you could conceivably write that in any of 4 factorial or 24 different orders. Okay, let's keep going. A couple more here. Let's try another one. Again, trying to make these things a little bit harder and a little bit more like what the homework's going to look like. Let's try 4x minus 2y cubed. Now you could, if you wanted to, multiply 4x minus 2y times 4x minus 2y times 4x minus 2y. That's a lot of work. I'd rather think of this as 4x plus negative 2y, and that this is my A, that's my B, and then work with things from there. Now this is going to require some more simplification at the end. That's okay. We'll start out with 4x cubed, and then we'll do the b as well. That'd be negative 2y to the 0 power plus. Now we're going to decrease the powers on the first term. So it's going to be 4x squared times negative 2y to the first power, and then 4x to the first power and negative 2y squared. Finally, 4x to the 0 power and negative 2y cubed. So each time you move over from one to the next, you're going to decrease the exponent on the a term and increase the exponent on the b term. Now, if you look at each of these terms before I simplify it, these exponents should add up to the exponent on the outside here. 3 and 0 is 3. 2 and 1, 1 and 2, 0 and 3, all add up to 3. So that's a little double check of your work. Now, that doesn't exactly work here, but it does work up here. This would be a 3 and a 0, a 2 and a 1, 1 and a 2, etc. It works back here. 5 and 0, 4 and 1, 3 and 2, 2 and 3, 1 and 4, 5 and 0. So there are little things you can do to double check yourself. Let's see if we can't finish this one up. I need to put in my coefficients. Like before, it's going to be 1, 3, 3, and 1. I got to be a little bit careful here. I need to cube this out. That's going to be an x cubed, but 4 cubed is 64. So 64x cubed minus 2 times, well, 4 squared is 16. So minus 2 times 16 is going to be negative 32 times 3 is going to be a negative 96 x squared y. The next one's going to be positive. So 3 times 4 is 12 times negative 2 squared. Well, first things first, negative 2 squared, is that going to be positive or negative? Do I get rid of the negative when I square that? The answer is yes. So it's really going to be 4 times 12 is going to be 48. How many x's do I have? Just 1. How many y's do I have? 2. Finally, the last one. Remember, that's gonna disappear. That's just gonna be a 1. So I'm left with negative 2 cubed, and hopefully you're getting negative 8. Good job. Like that. So these work out pretty nice if you're using Pascal's triangle, but Pascal's triangle can be a little bit of a pain if you have other types of problems. So for instance, I could be asked to find x plus 3y to the 30th power. Whoa, I guarantee you don't want to work to write 30 lines of Pascal's triangle here. That would take you way longer than anything else. But the good news is that they want the first 3 terms. And so let's just do the first 3 terms. And to that, let's look back at Pascal's triangle and indeed his formula. So there we go. Let's look down at this line right here. Just a second here. Here we go. This line. And notice all we need is the first 3 terms. So I need this one, and this one. So in our particular case, n is going to be 30. So let's keep that in mind as we look at this latest example. Back over to here. I've got my A here, and this is my B. So I'm going to start with x to the 30th. So x to the 30th times 3y to the 0. That should be 30, not 3. So x to the 30th, 3y to the 0 plus x to the 29th times 3y to the 1st, and then x to the 28th times 3y to the 2nd. Now the big thing is I need to come up with the coefficients, and I don't want to go all the way down with Pascal's triangle. Don't want to do that. But when we look back at this, we notice that that second coefficient is just going to be n. And n for us in this case is 30. The first coefficient is 1. So that's pretty good too. So let's see if we can't figure out the rest of them. Or the last one then is just n choose 2. So it's going to be 30 choose 2. So, okay, good enough. So filling in the coefficients, I know that this is going to be a 1. This is going to be a 30, and this one is going to be 30, choose 2. Okay, so let's see if we can't figure out what that is. 30, choose 2. Should be 15 times 29 is my guess, but let's figure out what that is. And choose 2. Let's try 15 times 29, and yeah, I knew it. All right, 435. So this is going to be x to the 30th plus 30 times 3 is 90, x to the 29th, y to the first power, and then this was 435 times what? What do I get when I square this out? If you said 9, that's great. So I want to take and multiply that answer by 9, and I get 3,915. So plus 3,915 y, excuse me, I should do x to the 28th, y to the 2nd. Whew, not bad, not bad. There's one more like this that we'll do here. Hopefully you're hanging on with these. Just a quick word about Pascal. Even though this is called Pascal's triangle, it's not really his triangle. This was discovered a long time before Pascal. I have no idea how he got his name associated with it. But Pascal's triangle has a lot of cool things in it. For instance, you can see that these are so-called triangular numbers. You know, dots configured in such a way that they represent a triangle, like the setup for a game of bowling right here, 10 dots or 15 dots. Well, those are in Pascal's triangle. If you look down this column, you get the triangular numbers. So the next one after what we saw would be 21. And after that, can you guess? Yeah, 28. But how about this next column over here? 1, 4, 10, 20, 35. Well, there's a nice interpretation for that, so-called tetrahedral numbers. How many in your entire stack? So 1 and 3 gives you 4, 4 and 6 gives you 10, 10 and 20, or 10 and 10 gives you 20, etc. So those are your tetrahedral numbers. Oh, so that's kind of cool. Well, what else? Well, let's look. A name that I've mentioned in class a couple times is Fibonacci. A lot of things they could say about him, but probably one of the most famous things he's noted for is pondering, well, how many breeding pairs of rabbits would you have after a given time, assuming that each month you produce a new rabbit. So that was his thought process, and this is the sequence that he ended up with. In fact, it's a recursive sequence if you wanted to think of it that way, but that's a different video. To get from one month to the next, what you're going to do is add up the previous 2 months. So 1 and 1 gives me 2. 1 and 2 gives me 3. 2 and 3 gives me 5. 3 and 5 gives me 8, etc. Well, the Fibonacci numbers, and Fibonacci numbers are all over the place. Fibonacci numbers can be seen in Pascal's triangle a couple different ways. You can see them this way or this way. And then so much more. Powers of 11 are in Fibonacci's triangle. If you color the even ones, white and the odd ones black, then you get this kind of neat thing called Sierpinski's triangle. And it's just kind of a cool thing. If this were near Valentine's Day, we could talk about Sierpinski's Valentine. On and on. Product of these things has some similarities. Sums are powers of 2, but this was known a lot before Pascal ever wrote it. So back in 1303, in this text, it says Pascal's method was the old method. Here's Pascal's triangle in Japanese. and in Hebrew. So lots of cool things about Pascal's triangle. Well, let me finish up with one last one here. And that would be this. A to the 2/3 plus A to the 1/3 raised to the 28th power. Okay. Well, for this particular one, they just want the last two of these terms. Now, there's good news with the last two terms. We don't need Pascal's triangle. We don't need to plot out the binomial theorem because we kind of know the general form of what's going on with the last two here. So the last two, I'm going to end up with b to the n and a times b to the n minus 1 with a coefficient of n. So let's take stock of a couple things here for our particular problem. So this is my A, this is my B, and that's my N. And the last two terms are going to look like this. N times A to the first, B to the N minus 1, plus B to the N, like that. So let's see if we can't figure things out. N is 28. So 28 times A, which is A to the 2/3, times B, which is going to be A to the 1/3 raised to the 28th. And finally, B, which is A to the 1/3 again, raised to the 28th. I'm pretty sure they're going to want you to simplify things here. So let's start out with the easier part here. Oh, you know what? I cut a mistake here. That should be a 27. Should be n minus 1, right? 27 minus, it's going to be 28 minus 1 is going to be 27. So 28 a to the 2/3 times what? Well, what's going to happen when I remove the parentheses? What do these exponents do? Do they multiply or do they add? If you said multiply, kudos to you. And I know 27 over 3 simplifies, but I'm not going to simplify that just yet. Over here, again, these multiply. 28 over 3. And let's see. When I multiply things at the same base, what happens with their exponents? So you're getting a nice little workout in your exponents here, aren't you? When you multiply things at the same base, you add their exponents. And maybe now you can see why I didn't simplify this to 9, is because leaving it like this, they've got like denominators. So we'll just add the numerators. 2 plus 27 is 29 over 3 plus a to the 28 over 3. Wow.
That was easy.
I hope this helps. Feel free to swing by in some of my Zoom meetings, get more help. Until then, see ya.